Hey everybody, I've got an interesting question for us to look at, and not only is this pertinent to this current unit, but next semester when we talk about electrostatics, we're going to be using this idea a lot. Okay, and that idea is what's going on if you start digging into the Earth. So let me give you a review of, let's say you have the Earth and you're out here somewhere, and I ask you to determine little g. Well, the equation is big G, mass of the Earth, over r squared. Okay. Now, you might notice a problem with that. Okay. If you start digging into the Earth, what about when you get to the center of the Earth? What's r there? Well, r is 0. What's something over 0? Well, that approaches infinity. Does that mean that the acceleration of gravity at the center of the Earth approaches infinity? No. So that is definitely wrong. So this equation is just fine when you're at the Earth's surface or outside the Earth. But if you try to dig into the Earth, this equation is not correct. It's invalid. So how do we figure out what little g is inside the Earth? Well, I'm going to do a different example first to kind of get you into the flavor of this. So let's say you have the Earth, but the Earth is hollow. So I want you to imagine that you have a shell. So this is the shell, and all the mass of the Earth is in that shell. So the mass and radius of this weird hollow planet is the same as Earth, but all the mass is contained in this shell. Okay. Now, if you are standing outside the Earth, you would not know the difference as far as gravity goes. You would not feel any different. So if the Earth were hollow or solid, as long as it had the same mass, G would still be this equation up here, and we'd still, at the surface of the Earth, G would still be 9.8 meters per second squared. All right. Well, what if you were to dig a hole through here and then put yourself, let's say, right there? Okay. What would your acceleration be then? Well, it turns out your acceleration would be 0. And here's why. All this mass, I'm going to kind of split this up into two halves here. All this mass to the left of that red line would pull you this way, okay? And all the mass to the right of that red line would pull you this way. Now, over here, there's more mass, but it's also farther away. On the right side, there's less mass, but it is closer to you. Those two effects balance each other out. So if you're inside that planet, gravity is 0, meaning you would float around in there and you would literally be weightless. So it'd be really fun. You'd be floating around in there. It's as if you're in deep, deep outer space. It would be the same idea. And you'd have this big, huge room to play in. Okay. Now, if we were to graph this, all right, so if we're going to graph the magnitude of little g versus r, a point of interest is the radius of the Earth, okay? If we are outside of the ball, your acceleration of gravity looks like that, and the equation is big G, mass of the Earth over r squared, the one you're familiar with. As you dig through the shell, the little g would drop, and then if you're inside the shell, little g would be 0. So there would be your graph of little g versus r. Okay, so that's if the Earth is hollow, all right? Well, what if the Earth is solid? Okay, now let's just pretend for a minute that there's no molten core, that instead the Earth is solid and you are able to dig a hole through it like so. So imagine you've got a tunnel. Let's put the tunnel at the center though. So imagine you've dug a tunnel that goes straight through the center of the Earth, okay? And let's say you're able to keep all the air out of that tunnel, so you don't have to worry about that. And you make a tunnel so that there's no lava, molten mantle, or core, or iron, or nickel, or anything in there. Okay. And let's say you lower yourself in. Now here we're in Chicago. This would be somewhere, I believe, in the Indian Ocean somewhere near Australia. Okay. So what would happen as you lowered yourself into the hole? Like what would your acceleration be if you were, like, let's say there, and here's the center of the Earth, right? This would be your radius at that moment, which would be less than the radius of the Earth. Okay. Well, here's the deal. If you're inside of there, you draw a sphere that includes the point that you're interested in. Okay. All the mass outside of that little red sphere I've drawn will cancel out. All the effects of gravity will cancel out, just like they did for the hollow sphere. Okay. So all this mass doesn't do anything. Okay. All of its effects cancel. What does matter is the mass that's inside that sphere that you drew. We'll call that M prime. Okay. That mass, it's as if you're now standing on a smaller planet that has that mass. All right. Now, how do we calculate that mass? Well, we can do a ratio. The mass of that blue sphere, which we'll call that M prime, over the total mass of everything, the planet Earth, okay, is proportional to the volumes that they enclose. Volume for a sphere is 4/3 pi r cubed. And this will be over 4/3 pi times the entire volume would be the radius of the Earth cubed. Okay, and over here, this is the mass of the Earth. All right. Now, obviously, the 4/3 pi's drop out, and you get the following. M prime is equal to the mass of the Earth times the ratio of the radii cubed. Okay. And then you still use your same equation for G. But now G is going to be big G M prime over R squared, which would be big G, and you plug all this stuff in for M prime. So that'd be mass of the Earth times little r cubed over radius of the Earth cubed divided by little r squared. And you'll notice, and by the way, important, little r and big R are different things. Okay, little r is where you're at. Big R is a constant. It's the radius of the Earth. Okay, so you get the following equation. If you are inside the Earth, you get big G, mass of the Earth. You get over radius of the Earth cubed. That's a constant. And then these partially cancel, and you get just a single r up there. R is your variable. What kind of equation do you have here? Everything else in that equation is a constant. So you have G equals some constant times R. Well, that's linear. Matter of fact, when R equals 0, when you're at the dead center of the Earth, what's little g then? Well, it's 0. In other words, all this stuff is pulling equally on you in all directions, and so the overall force is 0 acting on you, which means you'll have no acceleration. Okay, so if you were to graph this, okay, so here's little g versus r, and again, point of interest is the surface radius of the Earth. Okay, so if you're outside of this, your equation is little g equals big G, mass of the Earth over r squared, r being wherever you're at if you're outside the Earth. If you're inside the Earth, you've got a line. It's linear, and this is your equation right there. Now notice that this equation and this equation have the same value if you're at the surface. If you put r, if you make this RE there, and you make this RE here, those two equations end up being exactly the same answer, which they should because they have that point in common right there. So what would happen is if you were to lower yourself into this thing and be able to stop yourself right there at the center of the Earth, you would at that only at that one point you'd be weightless. Okay, and if you were to stop there, you would be stuck there. Then you wouldn't be able to go either way. Now, if you're somewhere like, let's say here, okay, halfway between the surface and the center of the Earth, well, this is a linear equation. If this is 9.8, well, if you were here, your acceleration would be about 4.9, okay? Now, in the next video, we'll talk about like what kind of ride would you have if you were to just drop yourself into the hole from the surface. In other words, if you weren't going to stop yourself, but instead you dropped yourself and let yourself move, what would happen? So that's going to be our next and final video for universal gravitation. And we're going to tie it into something else that you guys have already talked about. So I hope that video was interesting, and thank you very much.